Welcome to Calculus AB video for skill number 156. I can use calculus to sketch functions. Alright, since this is a video about sketching functions, there's lots of different aspects of functions we should refresh ourselves on how to find. So the first that we need to be able to find is the x-intercepts. Remember, the x-intercept is where the function crosses the horizontal axis. So at that point, y values are 0. So what you can do is you set the equation equal to 0 and then solve for x. And to find the y-intercept, there's only going to be at most one of them, and to do that what you want to do is let x be 0 and then solve for y. To find horizontal asymptotes, if they exist, remember a horizontal asymptote is what does the function approach as x goes to infinity. So you're going to take the limit as x goes to infinity for the function, and you'll also need to take the left one, so as x goes to negative infinity for the function. There does not necessarily have to be one. It's possible that there is one or even two horizontal asymptotes. To find a vertical asymptote and holes if they exist. And this one's actually a little bit more challenging, but first you want to find discontinuities and then identify what type of discontinuity it is. So if you have a discontinuity at A, you're going to take the limit as x goes to the A from the left and from the right, and if both of those are infinity, then you have a vertical asymptote, and if they are equal to one another, then you have a hole. So typically what's going on is this will occur with rational functions, and in pre-calculus we learned that what we do is we can factor the numerator and the denominator for our rational functions, and if you factor the numerator and the denominator, then maybe you'll have several different factors. If a factor like 2x minus 7 exists on top and bottom, they cancel each other out, and so we have a hole at x equals 7/2. Whereas if you get a factor which doesn't cancel out, like x plus 4, and this is x minus 3, x plus 1, because it doesn't cancel but it's in the denominator, we're going to wind up having a vertical asymptote at x equals -4. And personally, I find this is an easier way to think about vertical asymptotes and holes, but the calculus behind it is taking the limit as x approaches those values. Alright, to find the x-coordinates of critical points, what that means is we're going to set f prime of x equal to 0, and the critical points are whenever this is true and at discontinuities. So if our function was this one here, we'd also have a critical point at -4 and one at 7/2. Okay, let's take a look at the second page. So to find intervals of increasing and decreasing, we've learned that what you do is you have your number line and you're going to have your critical points, and then you're going to test f prime in each of these intervals. So this will tell you your intervals of increasing and decreasing. If f prime is greater than 0, then we're increasing, and if f prime is less than 0, then we are decreasing. To find the coordinates of the inflection points, what you want to do is you want to set f double prime equal to 0 and then test concavity. So when you have your potential point of inflection, you're going to test on each side. So f prime on each side, and if it goes from positive to negative, then it is a point of inflection, or negative to positive, then it is a point of inflection. We use this method to also determine concave up versus concave down. So like in this case, we are positive there, so if f double prime is greater than 0, we have concave up, and if f double prime is less than 0, we have concave down. And to find our relative extrema, there's actually a couple different approaches. The first derivative test tells us if f prime goes from positive to negative, then we have a relative max, or a local max. That's the first derivative test. The second derivative test says if f prime is equal to 0 and f double prime is less than 0, then we've got a case where it's concave down and we're going to have a relative max. Or if the f double prime is greater than 0, then we'll have a relative min, because we are concave up. So the red is your second derivative test, and then the black is your first derivative test. Okay, let's apply these to our problem set. Alright, so what we're being asked to do is find all the important information to sketch the function. So x and y intercepts, asymptotes, that would be both vertical and horizontal, finding the critical points, which will help us identify increasing and decreasing, and the inflection points, which will help us identify concavity. And then finally, what is our relative minima and maxima, and sketch it. And truly this is a wonderful comprehensive skill that is kind of testing all of the things that you need to know for this unit. So this covers 4 or 5 skills in one go. Let's take a look at problem number 2. Alright, the first thing we're going to do is we're going to find our x-intercepts. And x-intercepts occur when the function is equal to 0. So if I have this, if I'm going to set this equal to 0, one approach would be to factor it. So I have x squared times x squared minus 1, or if I factor it completely, x minus 1, x plus 1. So we have x-intercepts. I'm just going to write it down here at the bottom. X-intercepts at -1, 0, 0, 0, and 1, 0. So let's go ahead and plot those three x-intercepts. And then we are going to find our y-intercepts. Let's label this x-intercept. Then we're going to find our y-intercept. So the y-intercept occurs when we let x be 0. So we have 0 to the 4th minus 0 squared, and that is at 0. So we get our y-intercept at 0, 0, which we've already plotted. But there we go, y-intercept at 0, 0. Then we're going to ask ourselves, is there any horizontal asymptotes? So horizontal asymptotes, we will take the limit as x goes to infinity of our function, and in this case that equals infinity, so there's not one on the right hand side, and we take it from the left hand side, and we also get infinity. So no horizontal asymptotes. So I'm just going to write no HA. And then we will check for vertical asymptotes. And a polynomial is continuous everywhere, so there is no points of discontinuity. So there are no vertical asymptotes. Now we want to get into talking about our increasing and decreasing intervals. So let's set f prime of x equal to 0. So f prime of x is 4x to the third minus 2x, and if we set that equal to 0, we can factor, we get 2x squared minus 1 equals 0. And it looks like we have critical points at 0 and plus and minus the square root of 1/2. So we're going to have to create a sign chart, and I'm going to kind of pan over here to look at what's going on. So negative root 1/2, 0, and positive root 1/2. And we're going to plug in values to test. So we'll do f prime of -1, f prime of 1, and then the square root of 1/2 is, oh, let's just do 0.2. F prime of 0.2 and f prime of -0.2. And if we stick these values in, we will get a negative times a positive, so this is negative, and then we get positive, and this would be 0.2, this would be negative, and this would be positive. Because we see the sign change from negative to positive, we know that there is a local minimum here, and also a local minimum here, and then a local max at 0. So I'm going to go ahead and write that down over here. We have a local min at the x-coordinate is negative root 1/2, and we would plug that into our original function to get the y-coordinate. We also have one at positive root 1/2, and we plug that in to get the y-coordinate. I'll quickly do that. Plugging those into the calculator, I got a negative 1/4 for the y-coordinate, which means we could actually plot those points approximately where they belong. The square root of 1/2 is about 0.7, so we have something around there and there. We have a local max at 0, which we found because right here we're going from positive to negative. So that is going to be a local max, and we already know the coordinate at 0, so we can finish that local max at 0, 0. Finally, we want to find the intervals of concavity, so we need to take the second derivative. So the second derivative with respect to x is 12x squared minus 2, and if we set that equal to 0, we're going to get x is plus and minus root 1/6. So there's our turning point for concavity. And so what we want to do is, again, create a number line with root 1/6 as the points that we test. Oops, that should be a positive. So we're going to test 0, so f double prime of 0, f double prime of -1, and f double prime of +1. And we find that when we test these values, f double prime of -1 is positive, f double prime of 0 is negative, and f double prime of 1 is positive. So we can conclude that we are concave up from -infinity to negative root 1/6, and from positive root 1/6 to infinity we are concave down from negative root 1/6 to positive root 1/6. And I didn't write it in here. Let's make sure we get it in here. We were supposed to find the intervals of increasing and decreasing, so let's go ahead and write that down. We are decreasing from -infinity to negative root 1/2, and from 0 to positive root 1/2. And then finally we're increasing from negative root 1/2 to 0 and positive root 1/2 to infinity. Okay, we found everything. We've plotted a few key points, and now what we can do is we can graph our function. What we have is a curve that's going to pass through these points. I didn't draw it great because it's hard on the iPad, but you can see that what I've got is we have a function which goes decreasing to increasing to decreasing to increasing. It appears as though we are concave up, and then concave down, and then concave up. There's no horizontal asymptotes and there's no vertical asymptotes. So there we go. If we wanted to get a few more accurate points in, maybe we could evaluate the function at 2 and plot some points in there. 2 to the 4th is 16, minus 4 is 12. So yeah, it's already off the graph by there. So there we go. So because this is a fairly thick skill where we're combining lots of different skills that we've learned so far into one aspect of graphing, I'm going to save the remainder of the examples for demonstration in class, but I would go ahead and challenge yourself and try to work through some of the odd problems. We'll talk about the even ones in class. Thanks for watching. Alright, so hopefully now you're able to use all the various things we've learned this unit to sketch a function.